Hello, everyone. Good morning. So, today I'm going to talk about something which every Rails developer faces eventually, and that is performance slowness. So, we often expect our applications to be smooth and fast, but is that the reality always? Not sometimes. And what creates is the frustration. So imagine your life is going hunky-dory, and you get the calls from your users that your listing pages are taking minutes to load one single listing page. And you get frustrated. You still manage to fix that one issue, and your life is sorted again. But the real problem is not solving just one issue. The real problem arises when you get multiple such issues. For example, your search query is taking minutes to search one particular keyword, or the listing pages are taking time, or the Sidekiq batches are taking sometimes hours or days to finish one job. And that creates the user frustration, and not only to the users, but to you as a developer as well. It increases your infrastructure bills and the delayed features, because you're still firefighting your performance bottlenecks. So performance is not optional, it is the survival. So today, I'll be talking about the performance measurements and preventions. And when this happens, you get the temptation that maybe instead of Rails, I just rewrite that in Rust or Go. But rewrites are risky, and they are costly as well. So instead of doing that, you can put your application under the microscope and actually find out what are the bottlenecks. Hi, everyone. I'm Snehal Ahire, and I work as lead software engineer at Joe Software from India. And I've been working with Rails since 2018. So today, I'll be talking about the story about an application that we started in 2013 with Rails 3.2. And back then, the issues were different, because initially, when you start any application, the issues are different. 12 years later, you actually get into the performance issues, and your issues are different. So the code that looked innocent once turned into the bottlenecks. So working on multiple applications, I found out some underlying patterns which are very common, and I like to call them as monsters, the monkey monsters, and I'll be talking about them. So I'll be talking about the memory bloat, memory leak, and the database inefficient queries. Before we deep dive into all of these, let's go back to the basics. So every production-ready app should have these basic optimization techniques that you must have applied. For example, fetching the data. In this example, we can see that it is fetching all of the users. It loads all the columns in the memory, which is inefficient and slow. But it is actually using only the email and the name. Instead of that, we can do the select. Select only what you require. It looks very simple, and this code looks innocent. It works for example, thousands of queries, thousands of rows, but when you hit millions of rows, it is very inefficient. We all use pagination, but how you do the pagination makes a difference in your performance. So we use offset quite often, but it is really good for the small data sets. What it does, you actually see only a few records on your screen. But what exactly happens under the hood? It actually scans the entire data, and then it discards, and then gives you the required ones. So as you go further, for example, page number 100, page number 1000. So it is going to scan all of that records and then discard it, so which makes it inefficient for the large databases. So what you can do instead, you can use the key set pagination. So key set pagination only features the data that is required. So you so you don't need to actually discard. You don't need to actually fetch and discard. And it is index friendly, because The created at, and the ID are the index columns, and you can leverage the benefits of it. It gives a consistent performance because even if you go to the 1000th page, it is not going to fetch all of those records. So key set pagination is really good for the features like load more or the infinite scrolls. But the only caveat here is you cannot directly jump to, for example, page number 57, because it uses the pointers. Instead of skipping the rows, it uses the last row from the previous page as the starting point for the next query. So you cannot jump. So although I spoke about only the selects and the pagination that we often use, we all know that the application should not have the n+1 queries. In the development mode with Rails 7+, you can use the strict loading so that you don't even write the n+1 queries, even accidentally. Rails provides a lot of caching strategies, but here's a catch. Use caching only if your recomputational value is greater than the caching maintenance and the invalidation. Otherwise, cache will hurt you later. So far, so good. We spoke about the basic optimizations. So we did that as well. But then one day, I saw this disastrous entry out of memory. And when I looked at the graphs, I checked from the 48%, it directly jumped to 93%. Now, when you know that your application actually has only, for example, 50 MB of live objects, but your RSS is still showing you 800 MB, that gap, we often call it as memory bloat. Then, what do we do about it? Now we have found that 48 to 93 is a disaster. How to fix that? We look after multiple tools, and then I found my friend, Memory Profiler. So Memory Profiler gem gives you the memory allocations and the retained objects. It gives you the memory by gem, by the location, by the classes, by each line as well. So you know exactly what is actually consuming. And if you look at the graphs, the maximum memory is consumed by the array, strings, and the hash. That came to my mind. Why it is consuming so much of memory? Let's look into that, why the memory bloat actually happens. So as we all know, Ruby manages its static functions in the stack and all the dynamic allocations in the array hash, all the dynamic allocations like array hash in the heap. Now, inside heap, it manages the allocation with the multiple pages. Now, each page is further divided into the multiple slots. Now, when Ruby has to allocate one Ruby object, it looks for the free slot inside the page. For example, here we are trying to allocate 8 objects within one page. Now, let's allocate more objects. Here we have allocated 14 objects, and we still have one page. Now, we wanted to allocate more objects, but the page was full. So it asked for another page. But Ruby does not directly communicate with the OS for getting the pages. It communicates with the system allocator, that is malloc or gmalloc. So it communicates with the system allocator and gets another page and allocates the objects. Now, malloc internally manages, like Ruby, it has the arenas and the slots to manage the memory inside. And it expands internally as well. As the time grows, so garbage collector, it is going to free some of the objects. As we see, the blacks are the holes, and it creates the holes. Now, what's the problem? The slots are not adjacent to each other. So for example, I have 160 KB of object but the slots are not adjacent to each other, they are not next to each other. And it cannot allocate any of the slots. So it asks for another page to the system allocator. And then the pages go on increasing. So what we see, there is actually free memory inside the heap, but it is not in a good shape for allocating the objects. So this is what we call as heap fragmentation. And we go on with the more fragmentation because the continuous allocation and deallocation increases the fragmentation. Similarly, the way heap fragmentation happens, the allocator fragmentation also happens. It also suffers the fragmentation because it cannot merge two blocks which are not adjacent to each other. Because of this, in the multi-threaded environments like Sidekiq, you can configure malloc arena max to 2 or 4. The more number of arenas are there, more is the fragmentation. So this is one configuration you can definitely do for the Sidekiq jobs. Now, on the top of this, allocator retains more memory. For the performance reasons, it keeps the cache of the different size blocks so that the next allocation is instant. Then comes the garbage collector. Now, garbage collector doesn't immediately release the memory back to the system. Instead, it retains it with itself for the future allocations, which causes the process memory usage it to remain high even after the objects are no longer required. Here's a time when you can configure the garbage collector as well. Here, you can configure the max heap size, the heap growth factor. So more is the heap growth factor, less is the fragmentation. In Ruby 3.2, we have variable width allocation, which manages the slots not statically, but through the size pools. It is done for reducing the memory bloat or the fragmentation. But what if your code does not support it? It is not that effective. So let's look at some of the examples which actually cause the memory bloat. So here's a quick recap. Why does memory bloat happen? Your heap fragmentation, allocator reserving the extra memory, and GC holding the memory. Let's look at the examples. The high memory usage and the RSS growth. RSS is the resident state size, which your particular process uses it from the RAM. So this code looks very simple. You are loading all the users in the array. But instead of that, it is going to actually load all of the users. Instead of that, you can use the batches, and you can also configure the batch size. Even further, if you want to show that data on the screen, on the UI, so we normally fetch all the users in the Ruby and then convert them into the JSON. So that means it allocates a huge memory, and Ruby has to serialize everything. So instead of loading all the rows in memory, let Postgres do the job. So Postgres has the functions like row to JSON and JSON aggregate that can directly build the JSON on the database side. So we can leverage those features. Also, the CSV read, if you have just 10,000 rows, it is good. If you have millions of rows, it is just going to bloat your memory drastically. Instead of that, you can read line by line, or you can use the for each. Temporary object creations. So here inside the loop, we are trying to create date.today. So it is going to create new object for every iteration. Imagine this loop iterates millions of times. So it is going to create many objects. So instead of that, before the loop, just create that object and also use the freeze and reuse it in the loop. Another example of objects, temporary objects. We often use includes. So even in here, the array is going to get created in every iteration. These are very common practices. We just write this code. But when your application is at the start, it might not hurt you. But with millions of iterations, it creates all of these objects in the memory. So instead of this, you can use set for the faster retrieval and also freeze. Then the per record operations, like the destroy. Destroy is going to, of course, destroy all the associations, but it is going to load everything in the memory. Instead of that, you can use the delete all. It is the single operation, but it does not you use the callbacks or the associations. So you need to be mindful about it. So delete all the children first and then the parents so that you do not have any orphan objects. Again, regarding the update, if we do this, it is the per record query. It is going to hit into the n+1, and it is going to load all the records in the memory. Instead of this, we can use upsert, update all, upsert, all of these features which are in the single bulk operations. Here, the order has the association with the line items, one insert per row. But then again, same problem with multiple rows. It is going to create everything in the memory. Instead of that, you can use the insert or the upsert for the bulk queries. And you can also use the map to just previously fetch the data and upsert that in one query. So the quick checks to fix the memory bloat issues, you can use the batches, reuse the data, and freeze, so that the objects do not get created multiple times. So far, so good. We did the basic optimizations. We fixed the memory bloat problems as well. And then one day, I again saw this graph. The memory was hitting gradually like this. We got frustrated. And what do we do in the frustration? We just switch off the laptop, yeah? How many of you do that? Just, yeah? And restart, we feel, it worked. But does that actually solve your problem? Do you think that there was no problem? There was. If this happens, there's probably the problem of memory leak. Let's look at some of the examples why the memory leak happens. Your RSS grows. So you'll see that the RSS kept growing steadily with every call and the Sidekiq jobs, and it never goes down. Your heap objects stuck. Normally, objects get allocated and deallocated and freed. But in this case, if the count never drops, this is one of the reasons. Frequent GC pauses. So GC is working overtime to clean up, but since the objects are never released, the count never gets dropped. Also, you then hit the last hammer, you restart the process, and it works. But then these are the problems, these are the symptoms that you have the memory leak. Let's look at the basic examples that might lead into the memory leak. They all look so innocent at first, trust me, but then these are the monsters. Unbounded in-memory objects. Here, we're trying to calculate the discount and trying to store it in the class variable. But the class or the global variables, they grow unbounded. Because with each iteration, with each call, it is just going to append the data. But garbage collector cannot release it because the class variables or the global variables are always referenced. So imagine how much it can grow. So instead of storing this into these kind of variables, you can just write a method. The result is local, and you can just return the values. And these are freed automatically after the use. Another example, we use closures. But the closures do not capture the values. It captures the variables. So if you are going to pass the big values or the large objects, it is never going to get released. So instead of that, you can only pass what is required. So here, you actually only need the size. So instead of passing the whole array, you can calculate the size, and you can just pass the size. So it extracts only the required data, and it just pre-compute and pass the data. That's about the memory leak examples. We did these kind of simple changes, and what we got, let's look at it. So before optimization, we were taking 788 MB of memory, and which got reduced to 459. This is a 42% reduction. Before, it was taking 11 million objects, and it got reduced to 2 million. And the performance time, as we can see, is from 2 minutes to 10 to 20 seconds, which gives me 42% reduction in the memory and 80% fewer objects. Is that all about? No. Along with this, we need to also tune the database queries. So let's look at I'll just walk you through an example of one of the queries in the database. So let's look at this. We have the simple where with the ID and the state. And to profile the database queries, we actually use the explain, analyze plans. How many of you use explain, analyze in the Postgres? That's a good count, yeah? So when I also looked at the explain, analyze, if you see the execution time is 2800 milliseconds. And it is doing the parallel sequential scan, okay? Then I added one more query, is feature true, and this gave me the execution plan to 0.7 milliseconds, and it used the index scan. Magic? Is that magic? Because from 2800 milliseconds, it has come down to 0.7 milliseconds. And from parallel scan, it used the index scan. There's no magic in this, because we were using this query, this index. So this is the partial index that we were using. But your indexes will help if the query includes the index conditions. So if you neglect these kind of points, you will always see the high execution times. So these are the tiny features or the neglected points, but they create huge performance differences. Not only this, but even if you have one feature or one problem in your application, that will slow down your entire application. So special problems need real solution, need special solutions. For example, if you have a lot of static data and you need to compute it using a lot of joins of the past records, instead of joining from 7 to 8 tables and getting that data, and you don't want to go with the read replica because then it will again get into some of the complications. If you don't want to do that, you can leverage the features of Postgres. You can use the materialized views. It is a physical table. You can just store the data, and you can utilize that instead of computing again and again. If you're searching on multiple columns, you can again leverage some of the features of Postgres, like the TS vectors. With TS vector and with the gin indexes, you can do the search. You can create the vector with multiple columns and search directly with the vector. In Sidekiq, if you want to auto-scale it, you can do the latency-based queuing. So with latency-based queuing, you can actually have the multiple queues based on their latencies, and that will help you to auto-scale the Sidekicks as well. For faster retrievals of the JSON columns, you can use the specialized indexes like gin indexes. So again, like there are multiple types in the operators in the gin indexes, but then these kind of features or the functionalities given by the databases will help you to enhance your features. So, what are the key takeaways from all of these aspects? Profile, measure before optimizing. So don't rely on your gut feelings. Use the tools to actually find out the bottlenecks. Leverage the database capabilities. So indexes, aggregations, bulk operations, these are all designed to do the heavy operations. So don't try to reinvent them. So instead of make the use of them. Find the data patterns. Think about how the data generally gets retrieved, processed. Even the small inefficiencies add up to the scale. Collaborate on performance. So performance is not just one person's job. Share the responsibilities across team and celebrate when you get to the better. Bake the performance into the workflow. Set the budgets, monitor it throughout. Don't treat performance at the afterthought. It should be always the part of your design and the build and when you ship the features. So that is all about it. To tackle any kind of performance issues, you need to look into the various aspects to fix it, and not just once. So instead of trying to rebuild everything into some other language, put your application under the microscope and look at what are the bottlenecks. You can connect it here. Thank you so much for joining my talk. Thank you so much.